Buenas tardes, bienvenidos a otro martes de coloquio del Instituto de Ciencias Aplicadas y Tecnología. En esta ocasión tenemos la presencia del doctor Nadir Jeevanjee. ¿Is that right? Jeevanjee? Ok. Él nos acompaña de la NOAA en los Estados Unidos, que es la Asociación Nacional de Oceanografía y Atmósfera. La charla de hoy va a ser en inglés, entonces voy a presentar al profesor Jeevanjee. Welcome, Dr. Jeevanjee. We are expecting your talk about the climate sensibility, the water vapor feedback, and the Simpson's law. I'm going to introduce you to the audience. Dr. Nadir Jeevanjee studies the physics of clouds, radiation, and climate using a hierarchy of approaches ranging from pencil to paper theory to comprehensive computer simulations. He's currently a research physical scientist at the National Oceanographic and Atmospheric Association of the United States in the Geophysical Fluid Dynamics Laboratory. Prior to this, he held postdoctoral positions in Princeton Geosciences as well as in Princeton's AOS program, and got the PhD in 2016 from the UC Berkeley, working with David Romps. Dr. Jeevanjee have a keen interest in communicating climate science to other scientists as well as the public, both on his own and also as a member of the Climate Up Close. He also collaborates with Sea Change Conversation. Before turning to climate science, Dr. Jeevanjee studied mathematical physics for many years, during which he authored the textbook An Introduction to Tensor and Group Theory for Physicists. So, Dr. Jeevanjee, once again, welcome, and we are ready to hear you.
Terrific. Thank you. I'll share my screen. Let's see here. Okay, I assume you can see the presentation and hear me okay?
Yeah, great.
And can you see my cursor on the screen?
Yeah, oh, yeah, you can see it.
Okay, excellent. Yes, so thank you for the introduction. Today I'm going to tell you about work that's done with a number of collaborators, including a couple of younger students and postdocs, including Brett McKim, who's a PhD student at Exeter, and Yi Zhang, who was a student at Princeton and is now a Miller Fellow at UC Berkeley. And I'll start with just a little bit more personal background, just to kind of tell you where I come from and why I'm sort of doing what I'm doing. So as Juan Carlos said, I got my PhD from Berkeley in physics in 2016. And I started out studying theoretical physics, mathematical physics. I even wrote a textbook on the subject. But then later, I ended up teaching a course taught by Richard Muller, who himself is also a physicist turned climate scientist, called Physics for Future Presidents. And that course kind of opened my eyes to the ways in which physics underlies the science of both climate change and renewable energy. And I got excited about the idea of applying my physics knowledge to these pressing problems instead of more esoteric issues and theoretical physics. And so I actually switched PhD advisors to working with David Romps, himself a former physicist, and we studied clouds and convection in the tropics. And here's a picture of a simulation of the kind I used to run during my PhD. And then I came to the Geosciences department in Princeton, and I shifted foci a little bit and started thinking about the greenhouse effect. And it's that work and the outgrowths of it that I'm going to talk about today. And after a few years there, I then crossed the street, still in Princeton, to the Geophysical Fluid Dynamics Laboratory, where I now work. But the point of telling you this background is that I'm really a physicist at heart, and I imagine many of you here in the audience have a similar background, and so that really colors my approach to climate science, trying to understand things from a fundamental level and build a bit of a ground-up understanding of how the climate system works. Now, sort of the timing of today's talk is interesting. So as many of you know, the Nobel Prize in Physics was announced late last night, early this morning, awarded to people who worked on the foundations of quantum information. It turns out that last year's prize, as you probably know, was awarded to 3 scientists for their work relevant to climate change. And in fact, the first one on the list, Suki Manabe, was a scientist here at GFDL. So of course, I was here at the time. That was an incredibly exciting time to be here at GFDL. And the Nobel Committee cited his work exploring the interaction between radiation balance and the vertical transport of air masses. So what does that mean, and why is it so important for understanding climate change? So what Manabe did was build a one-dimensional model of what became to be known as a radiative convective equilibrium. And so the paper is shown here on the left, and a key figure is shown here on the right. And what this model does, it just predicts one thing, which is the temperature profile of the atmosphere. And that's what's shown here on the right. And the reason it's called radiative convective equilibrium is that, the way the atmosphere works, and Manabe was able to model this with, simply but with fidelity, is that in the bottom layer of the atmosphere, in the lower, say, up to about 100 millibars, the lower 10 to 15 kilometers, you see that the temperature profile has this constant slope. And the slope is actually set by convection, right? This is the part of the atmosphere, the lower atmosphere, the so-called troposphere, where you have weather, you have thunderstorms, you have convection. And this convection actually has a characteristic slope of temperature versus pressure that goes with it. And it's actually very easy to understand. It's just the temperature profile you'd get from an air parcel if you lift it up from the ground to lower pressures, and it expands and cools just the way air coming out of a pressurized bicycle tire would cool. And the higher up you lift it, the more it expands and cools, the colder it gets, and that gives you a temperature profile. And that's essentially the exact temperature profile that you're seeing here. And in fact, you can write down an analytical expression for this using undergraduate thermodynamics. So convection sets the slope of the temperature profile in the bottom part of the atmosphere. But then in the upper part of the atmosphere, the stratosphere, above, say, 15 kilometers or so, you're not really feeling the influence of the surface. You don't really have much weather. That's why planes fly in the stratosphere, is because you don't really get much weather. And so convection plays a limited role, and it's really radiative processes, absorption of sunlight, of ultraviolet by ozone, emission of infrared by CO2 and other gases. It's that interplay which sets the temperature profile up there. So to really understand the full atmospheric temperature profile, you need radiative and convective processes. And that's what Manabe was able to model. And then if you look here, you'll see that Manabe used a few different CO2 concentrations. So he was really performing some of the earliest global warming experiments. And you see a cooling of the stratosphere, which we have observed, as well as a warming of the lower atmosphere and of the surface, which is a little bit harder to see. But it's there, and it's significant, and it's the global warming that we're all concerned about right now. And so when Manabe did this experiment, he had to make a choice. There are 2 ways to run these experiments in his model. One way was because not only is CO2 an important greenhouse gas, but water vapor is an important greenhouse gas. And so when running his simulations, he has to make a choice about how to specify the water vapor. Should he fix the absolute humidity? So this is denoted by the variable Q. And this is just the kilograms of water vapor per kilogram of air. And so should he fix that even when the temperature in the simulation is changing? Or should he fix the relative humidity, which is Q over the saturation value of Q? And the saturation value is an exponential in temperature. This is this Clausius-Clapeyron relationship, which many of us are familiar with, that the saturation vapor pressure of a gas goes up with temperature. And it turns out that it's reasonable to assume that one should fix the relative humidity. This is in fact what we see in the seasonal cycle, where relative humidities stay roughly fixed. And when you do that, then when you warm, you get more water in the atmosphere, and this is what has become known as the water vapor feedback, is when you fix the relative humidity and allow the atmosphere to moisten as it warms. And when Manabe did that, he found, and this is in his abstract, that the climate is twice as sensitive to changes in CO2. And in fact, when he doubled CO2, he got a temperature change of roughly 3 Celsius. And that's a number that's really stood the test of time. And I'm not going to talk that much more about Manabe's paper today in this talk, but there's a paper that we wrote that sort of reviewed why this work was significant that's just come out in the bulletin of the American Meteorological Society. And Isaac Held, who's a co-author, is a senior scientist at GFDL and was a former PhD student of Manabe's. All right, so climate sensitivity, or which we define as just how much the climate warms for a doubling of CO2, that's sort of this central quantity in climate science. It's the quantity whose uncertainties we want to narrow and that we want to understand better. So how do we quantify it? So the way it usually works is you think about the energy balance of the planet. You've got incoming solar radiation, which if you account for reflection by clouds and ice, you get a net incoming radiation of about 240 watts per meter squared. And this has to be balanced by the outgoing so-called long-wave radiation. That just really means thermal infrared, essentially black body radiation. And this is the planet's energy balance, that the incoming sunlight is balanced by outgoing thermal radiation. And so if you now then perturb this balance by changing the outgoing long-wave radiation because you increase CO2, and you've reduced this outgoing long-wave radiation, the amount that you reduce it by is called F. It's the forcing, also in watts per meter squared. So if you force the system by changing CO2, and of course we've gone from 280 ppm to over 400, so a factor of about 1.5, giving us a forcing of roughly 2 watts per meter squared. When you do that, then that's going to do some warming in the system. And the amount of warming you're going to get is exactly what's needed to bring the planet back into balance. And you can write down a simple equation that just says that whatever the derivative of the OLR with respect to surface temperature is, if you multiply that by the change in surface temperature, that must equal the forcing, which was the initial reduction, to bring things back into balance. And so the point of this equation is that the change in surface temperature, delta Ts, is determined by two things. How strongly you force the system, F, and then how sensitively it responds, this derivative, which we're calling lambda, and which is known as the feedback parameter. And so these are the two key quantities when we think about climate sensitivity. The climate sensitivity is determined by the forcing and the feedback. The rest of this talk is going to focus on the feedback and simple ways to understand that. It turns out there's also simple ways to understand the forcing, and there's a paper that came out a couple years ago that explains that if you're interested. And just as a note, here we're sort of ignoring the fact that you can also get changes in S because you can melt some of the ice, you can change the cloudiness, so you can change the reflectivity of the Earth. But that's sort of a second order effect. The first order effects are really about what happens in the infrared, and that's where we're going to focus. All right, so we want to understand what sets this long-wave feedback parameter lambda and what role the water vapor feedback plays. So to quantify this, let's start out with just a sort of simple textbook, no feedback black body model of lambda. And so, as we said, if you model the Earth as a black body at some characteristic emission temperature, then again you can use undergraduate thermodynamics and just set the OLR, the outgoing long-wave radiation, equal to sigma t to the fourth. That must equal the incoming sunlight. We know what S is, and so we can solve for this effective emission temperature, and it's about 255 Kelvin, or minus 18 Celsius. So that's quite cold, and of course it doesn't represent the surface temperature, it's really representing an average temperature of the atmosphere. And that's actually a pretty accurate, vertically average temperature. So if you take this model seriously and you compute the derivative of the OLR with respect to the surface temperature, well, it's just 4 sigma t cubed, and that gives you a number something like 3.7 watts per meter squared per Kelvin for the feedback parameter. And that's telling you again, of course, it's this derivative, so for every degree Kelvin of warming, how much extra emission to space do you get? What did Manabe get? When he included the H2O feedback, and the fact that the sort of emissivity of the planet is changing because you're adding more water vapor when you fix the relative humidity, he got a very different number, differed by a factor of 2. So he got 2 watts per meter squared per Kelvin. So that roughly doubles the sensitivity of your model, right? If you half lambda, you're doubling the sensitivity. And again, just to reiterate, this is an infrared clear sky feedback. We're not incorporating the effects of clouds or changes in ice, but this is the dominant effect. So this leads us to the questions that we're going to try and address in this talk. Where does this number come from? Can it be understood from first principles? And that's where the so-called Simpson's law is going to come in. And also, how well has this number held up since Manabe made this first estimate over 50 years ago in just a one-dimensional, highly idealized model of the planet? And so we'll turn to this top question here first. And it turns out that this number, this feedback parameter of 2 watts per meter squared per Kelvin, is actually quite ubiquitous. So it turns out to show up in observations. And so what's shown here is a histogram of data from satellite observations. It's a 2-dimensional histogram with axes of surface temperature and clear sky outgoing long-wave radiation. And so the brightness of the point, the brightness in the plot just tells you how many satellite data points. It tells you the density of satellite data points in that region. And what you find is that the satellite data points really lie along the line. They don't follow a sigma t to the 4th scaling. They really are linear. And this is purely just plotting satellite data. And when you evaluate the slope, it's 2.2 watts per meter squared per Kelvin. Very close to this 2 watts per meter squared per Kelvin that Manabe found. It also turns out that this number turns up when you run global climate models. So these are these very sophisticated models that simulate the fluid flow of the atmosphere and the ocean. It's what we build here at GFDL where I work, and in a number of other modeling centers around the globe. And so what's shown here is, again, the clear sky outgoing long-wave radiation versus surface temperature. And now each different color is a different model from different modeling centers around the world. I think there's 9 or so models shown here. And each dot is a single year, is the average over the globe and over a single year from a simulation of global warming. And so for a given model, a different color, you can see that the simulation is warming, the temperature is increasing, and this clear sky long-wave radiation that's headed out to space is going up. And if you compute the slopes of these curves, it turns out that the slopes are very consistent across the models, only about a 5% spread, and it's very close again to this 2 watts per meter squared per Kelvin number. So this number also holds not only in satellite data that are sampling regions across the globe, but it also holds in the global average under global warming. And finally, if you kind of turn back to Manabe's 1D calculations, but redo them with modern tools, and this is something that was done by my student Brett McKim, you get something similar. And what Brett did here is he took single columns, just like Manabe did, like I showed earlier, but he specified different values of the RH, and he took different baseline temperatures. And for each combination of an RH value and a surface temperature value, he increased the surface temperature by 1 to see how the OLR would change, and that gives you a value for the feedback. And it's the feedback that's plotted here both in contours and as a heat map. And if you look at this, what you see is that it's this 2.2 contour that really dominates most of the figure. Things start to change a little bit when you get to these much warmer temperatures, and that's something we can talk about. But for most of the temperatures that are relevant for the globe, you again find that DOLR DTS is something around 2 watts per meter squared per Kelvin. And so if we go back to these research questions and ask how this value is held up, it's actually held back remarkably well. You find this value in observations, in global climate models, and even in modern versions of this of Manabe's original calculation. All right, so that's sort of the the first main point of the talk. The second, we'll dig a little bit more into the fundamental physics and ask, how do we understand this value? And what is really happening in the water vapor feedback that makes climate more sensitive, doubles the sensitivity of a climate relative to a more naive estimate. And so to do that, we're actually going to have to understand a little bit about how the greenhouse effect works, focusing on water vapor, as it is the most important greenhouse gas. We can talk about the effects of CO2 in the Q&A. And the key point here is that, water vapor has the absorption of water vapor varies depending on where you are in the infrared spectrum. And so there's a spectral dependence of the greenhouse effect, which we have to understand. And so we'll start by just plotting the absorption spectrum of water vapor. This is from a one-dimensional line-by-line radiative transfer model. It's kind of a benchmark model. And all these wiggles that you see here are due to all these quantum mechanical spectral lines that you're likely familiar with. And this is actually already a smooth plot. And what I'm showing here is the absorption cross-section in effective area per unit mass as a function of wave number. It's measured in inverse centimeters, but it's proportional to frequency. So you can think of this as a frequency axis in the horizontal. And what you see is that there's many orders of magnitude variation in how strongly water vapor absorbs throughout the infrared spectrum. And in particular, there's this region in the middle where water vapor absorbs quite weakly. And as we'll see in a moment, water vapor is actually, it's absorbed so weakly that it's actually transparent in this region. What we're plotting next is the so-called optical depth. And this is now a two-dimensional plot as a function of pressure and again of wave number. And optical depth, what it is, I'll give you a formula and give you an interpretation. At any given height, it's just the integral from the top of the atmosphere to that height of the absorption coefficient, which depends on frequency, times the absorber mass. And the absorber mass you measure in kilograms per meter squared. And when you multiply these two numbers, you get something dimensionless. And the interpretation is quite simple. It's just the total effective cross-sectional area of absorbers above you divided by the actual area of your column. And what I've plotted here in the black line is the tau equals 1 contour. And now, why did I do that? Because it turns out that the tau equals 1 contour is really where photons are able to escape to space. And so what I've drawn here on the left is a distribution of molecules increasing exponentially downward, which water vapor does because of Clausius-Clapeyron. And then I've plotted the associated optical depth profile, including the intercept with tau equals 1. And what you can kind of just get pictorially from this is that when tau is much less than 1, your emitters are very scarce. And so they have a hard time emitting much radiation to space because there's not very many of them. Their density is low. When tau is much greater than 1 down here, you have a high density of emitters, but their view of space is blocked. Any photon that they emit is going to get reabsorbed. And so it's really tau equals 1. It's at this sweet spot, this transition zone from scarce to dense, where you are really able to emit a significant number of photons to space. So that's where emission to space maximizes. And indeed, if we plot the emission to space, and so that's what's shown here, is where in both pressure and frequency space photons are emitted to space, you find that it lights up exactly along this tau equals 1 contour. You may ask where this part of the tau equals 1 contour is, and it's actually there if you squint, but the Planck function is very weak over on this side of the thermal infrared. This is kind of the very high wave numbers, and so you just don't get any emission because of the way the Planck function works. And what you also see looking at this tau equals 1 contour is that in the window, you really are emitting from the surface. The atmosphere is transparent, and so that's why we describe it as the water vapor window. So now once we understand that, we can turn to this very special behavior of water vapor called Simpson's law, and this is what leads to the water vapor feedback. So what is Simpson's law? Well, I showed you this expression for optical depth as an integral. And if you integrate that for water vapor, then you get this expression. The tau goes as the absorption coefficient times the relative humidity times this Clausius-Clapeyron exponential. This is what goes inside the integral. When you integrate an exponential, you still get the exponential. So this is how the optical depth scales. And for any given frequency, we're interested in the tau equals 1 level. But this equation is so simple that this tau equals 1 level for a given frequency is going to occur at some preferred temperature. And so what that says is that any frequency is associated with a preferred temperature no matter what the surface temperature is. So in any climate, a cold climate or a warm climate, or in the Arctic or in the tropics, a given frequency is always going to be associated with the same temperature. And that's a consequence of this Clausius-Clapeyron scaling of water vapor. And so this leads to Simpson's law that as long as the relative humidity is not changing, the emission you get from H2O at a given frequency doesn't depend on the Earth's surface temperature. But that sounds sort of paradoxical. That's saying that, it sounds like this is saying that if you warm up the Earth, you won't get any more infrared light to space. So how can the Earth's climate be stable? So, when George Simpson formulated this just about 100 years ago, this seemed paradoxical, and so this became known as Simpson's paradox. Of course, the way out of this is the water vapor window that we were just talking about. And so to give you a feel for that, I'm gonna again run a one-dimensional model like Manabe's, and it's going to be spectrally resolved. So the horizontal axis here is frequency or wave number, and I'm going to plot emission temperatures. So the tau equals 1 level, and the emission temperatures are increasing downwards, just the same way that temperature increases downwards in the real atmosphere. So this is my vertical axis. And if I take a column with a surface temperature of, say, 270 Kelvin, so that's relatively cold, here's what the emission temperatures look like. In this window region, the emission temperature is the surface temperature because it's the surface that's emitting to space. But on either side of this in spectral space, you're emitting from water vapor molecules that emit from higher up in the atmosphere and emit at a colder temperature. But the key thing is now what happens if I take a column with a larger surface temperature, say of 280 Kelvin. If I do that, then I get this light blue line. And what you see is that where you're optically thick and where you're emitting from water vapor molecules in the atmosphere, the emission temperature doesn't change, just like Simpson's law says. But if I look in the window region, right, the temperature has now increased. The emission temperature has now increased from the old surface temperature to the new surface temperature, and so now I am getting more infrared to space, but only in the window. So the key is that Simpson's law applies where H2O is optically thick, where tau is much greater than 1, but not where tau is much less than 1, and the atmosphere is transparent. And this continues to hold as I increase the as I increase the surface temperature to 290 Kelvin, or even up to 300 Kelvin, though you can see it starts to break down at this temperature and the window starts to close. But these are around the highest temperatures that you see on Earth. All right. So now that we have some familiarity with Simpson's law, we can come back to this 2 watts per meter squared per Kelvin number in the water vapor feedback and try to understand it at a more fundamental level. And so what we learned on the last slide is that because of Simpson's law and to a first approximation, and Simpson's law, it really isn't an ironclad law. It's sort of a 0th order picture, and there are correction factors to it, which you could even see in the plot from the previous slide. But again, we're pursuing a sort of first order, spherical cow type understanding of the problem. And so to first approximation, where you're optically thick, there is no change in the outgoing long wave with surface temperature. So this derivative is 0. But then in the window, you're just seeing the surface. And so the change in OLR with surface temperature is just given by the derivative of the Planck function evaluated at the surface temperature. And that's basically what we saw on the last slide. And by the way, here I am plotting this spectrally resolved feedback as a function of frequency or wave number. And the true feedback is plotted in black. And then this approximation that I have here on the left is plotted in purple. And you can see that in this idealized case, it's really an excellent approximation. And what this allows you to do is actually analytically estimate what the feedback parameter should be. Because this is the spectrally resolved feedback parameter. And so now I just need to spectrally integrate it. But the spectral integral is 0 everywhere except the window. So to get my feedback parameter, dOLR dTs, I just integrate this derivative of the Planck function over the window. And this is something that, well, it turns out it's hard to do strictly with pencil and paper. I don't think there's a closed form expression for the integral. But it's easy enough to do numerically in just a few lines of Python. And indeed, you find that this integrates out to 2 watts per meter squared per Kelvin. And so this number that Manabe obtained and that we saw was ubiquitous, kind of throughout climate science, can be understood very simply and something you can write down on a chalkboard. Furthermore, there's a very simple physical picture that goes with this, which is simply that, if I look at this plot on the right, for a regular black body, this lambda parameter, which is just the derivative of the Planck function, would be non-zero across the thermal infrared. But what the water vapor feedback does is that because you're fixing the relative humidity, Simpson's law then operates and it deactivates all these optically thick frequencies on either side of the window and essentially sets their feedback to 0. And so that's what the water vapor feedback is doing. It's deactivating frequencies according to Simpson's law. All right, so when we ask ourselves, can this value be understood from first principles? We have this, this fact, this Simpson's law, that the emission from water vapor molecules in the atmosphere doesn't really change with climate change. This appears to be a reasonable approximation and allows you to estimate things analytically. So that's most of the story I wanted to tell. But kind of getting back to the introduction, my background is as a physicist and as a theoretical physicist. And this work, is just a little bit of a slice of how one can try and take, a more theoretical, bottom-up approach to climate science. But this is, I think part of a much broader project that I and others are involved with. And in fact, some years ago, I gave some lectures at Princeton, 3 lectures on different topics in climate science that you can try and understand in a similar fashion. There's actually lecture notes on the archive, and these explore a wide variety of topics, not just what we've talked about here, but also, what role does the deep ocean play in global warming? What are the timescales of global warming, et cetera. And there's also an article that came out in Physics Today about a year ago that tries to apply some of this to, frontier problems in climate science. Okay, so just to summarize, Simpson's law says that when you fix RH, you deactivate optically thick frequencies, and so you don't get any change in the OLR there. And by doing that, that basically doubles your climate sensitivity, and it cuts your feedback parameter in half from the typical black body sigma t cubed value. And indeed, as we saw in the beginning of the talk, this effect is quite robust across observations and climate models of varying complexity. And that's all I have for today, and I'll be happy to end here and take your questions. Thank you.
Thank you so much, Professor, for your interesting presentation. So now floor is open for question, either for YouTube or here in Zoom. Anyone question? Okay, so Nasser?
Hello, Nadir. Wondering if you can put numbers to all that. So I'm thinking of the Sonora Desert compared to the Amazon. By what order of magnitude does the radiation loss of the space change, or vice versa, the absorption?
I see, just comparing different climates with different relative humidities. Yeah.
Exactly, yes.
Yeah, great question. So we can actually, if we go back to this plot, and maybe I'll make this a little bit bigger. All right. So it turns out that for, in the extratropics, outside of the tropics, it doesn't really matter where you are. You can see that for surface temperatures less than 280 and for a wide range of relative humidities, the feedback parameter doesn't change very much. And so that means that whether you're in the Arctic or over the North Atlantic Ocean or over the mid-latitude continents, you're not getting a lot of variation. But you asked about warmer climates. So say a tropical rainforest around 300 Kelvin, or a desert which is maybe even 310 Kelvin. And here you see that the feedback parameter does vary. And it can actually vary quite significantly, especially depending on the relative humidity, right? So if I went from, if I'm at say 305 Kelvin, if I go from a relative humidity of 40% to 80%, I go from a feedback of 2.2 down to a feedback of 1.4. So that's almost a factor of 2 in the local sensitivity, right? You wouldn't feel that locally because the sensitivities of all these different regions of the globe get swirled together by the atmospheric circulation. So you wouldn't expect to feel these things at those locations, but you do get some geographical variation in that. And that's essentially because this water vapor window that I was talking about, which, let's see, you can see that. So I mentioned a little bit that you can start to see the water vapor window closing here, where the emission is no longer entirely from the surface, but it's from temperatures a little bit lower than the surface in the red curve. the water vapor window does start to close. And at these temperatures, it's very sensitive to the relative humidity. So all these curves that I'm showing here were at a relative humidity of 75%. But once you get up to this high surface temperature, if you start doubling or halving the relative humidity, then the window will close and you do get a sensitivity of this number, this feedback parameter.
Okay, thank you.
Thanks.
We have another question from YouTube. Camilo asks, what kind of satellite observations can help to observe the change in the sensitivity? Do we have observation of this change? Is this included in the usual climate models?
That's a great question, and it's actually something that people are working on right now. I mean, I have a paper on my desk that I'm reviewing at the moment that looks at satellite measurements. Basically, we're just getting to the point now where we have a long enough satellite record, because the satellite measurements of the top of atmosphere radiation really only started in the late 70s and early 80s. So we've finally got long enough measurements where we can sort of look at variability over that record, and there's enough signal to noise that we can start to see, essentially this feedback parameter that you see here, spectrally resolved in this upper right panel. You can start to see that in the satellite data. That's right, and it is teaching us things, and we are able to compare it to models because we can make the same figure from models. To see our models, are they simulating the right distribution of relative humidity, the right changes in relative humidity, things like that.
Okay, thank you, Professor. So do we have another question or comment, either in Spanish or English? Here, YouTube. Someone else? Okay, so I guess we don't have more question for now, but the video of your presentation will be available at the YouTube ICAT site. So we're going to provide you with one copy of this video. So we only have to no question. So we thank you, Professor Nadir, for your interesting presentation. We're going to send you the sorry, I mute myself. We're gonna send you the diploma of your for your participation in the colloquium, and I'm gonna speak in Spanish now. Si no tenemos alguna otra pregunta de los participantes, podemos dar por concluido el coloquio de hoy. Agradecemos al doctor Nadir Jeevanjee por su presentación y nos vemos el próximo martes. Thank you so much, Professor, and we keep in contact.
All right, thank you.
Bye.
Appreciate it. Bye-bye.
See you, everybody.